Somewhere north of Preston, in the green hills of Lancashire, there is a curve in the railway that has been there since 1846. It bends gently to the left, following the contour of a valley that Victorian surveyors chose because dynamite was expensive, and parliamentary approval for straight routes through wealthy estates was nearly impossible to obtain. That curve, and 10,000 others like it across Britain, Europe, and the world, represents a decision made by men who never imagined trains traveling faster than 40 miles per hour. For over a century, those curves dictated the speed of every locomotive that passed over them. Then engineers asked a deceptively simple question. What if the train could lean? Stand on a railway platform as a conventional train rounds a bend, and you will see the carriages sitting perfectly level on tracks that are themselves banked slightly toward the inside of the curve. That banking, called superelevation and cant, is the oldest solution to the physics of cornering. When a train enters a curve, centrifugal force pushes everything inside the carriage toward the outside of the turn. Passengers feel pressed against armrests. Coffee slides across the tables. At high enough speeds, the train itself can derail, its wheels lifting off the inner rail as momentum overwhelms gravity. The mathematics are unforgiving. Centrifugal acceleration equals velocity squared, divided by the radius of the curve. Double your speed and you quadruple the outward force. A curve designed for 60 miles per hour becomes dangerous at 90 and potentially catastrophic at 120. Railway engineers understood this from the beginning, which is why they banked their tracks, raising the outer rail above the inner rail so that gravity would pull slightly inward, counteracting some of the centrifugal force. The angle of this banking determines the equilibrium speed, the velocity at which the forces balance perfectly, and passengers feel pressed straight down into their seats rather than sideways. But superelevation has limits. Bank the track too steeply, and slow trains will tip inward, their wheels grinding against the lower rail, freight loads shifting dangerously. Every curve on a mixed-traffic railway represents a compromise between the needs of express passenger services and lumbering goods trains. The resulting cant deficiency, the difference between the banking needed for high-speed operation and the banking actually provided, translates directly into discomfort for passengers and stress on infrastructure. By the 1960s, with airlines capturing the lucrative business travel market, railways faced an existential choice: build entirely new lines with gentler curves, like the French and Japanese, or find a way to make existing tracks competitive. Italy chose the latter path first. In 1967, two engineers at Fiat Ferroviaria, Franco Di Maio and Luigi Santanera, filed a patent for a railway carriage that could actively tilt its body into curves while its wheels remained on conventionally banked track. The concept was elegant. If the track provided 6 degrees of superelevation and the carriage body tilted an additional 8 degrees, passengers would experience the equivalent of 14 degrees of banking, enough to take curves 30 to 40% faster without discomfort. The wheels would still interact with the rails normally, but the passenger compartment would lean like a motorcycle rider sweeping through a mountain switchback. The first prototype emerged in 1969, a single electric rail car that Fiat designated Y0160. It tilted using hydraulic actuators controlled by accelerometers that sensed the onset of curves and commanded the appropriate response. The Italians gave it a name that would become synonymous with tilting technology worldwide. Pendolino, the little pendulum. Across the English Channel, British Rail was pursuing the same dream through different means. The West Coast Main Line from London to Glasgow, laid out between 1837 and 1848, contained over 11 complete circles worth of curvature in its 400 miles. Every express service lost precious minutes, slowing for bends that Victorian engineers had inserted to avoid the estates of landed gentry and the expensive tunneling required by direct routes. In 1969, British Rail established a research division specifically tasked with developing a train that could negotiate these curves at speeds previously thought impossible. The engineers they recruited came deliberately from outside the railway industry. One had worked on guided missiles. Another came from the National Coal Board. They brought with them methodologies from aerospace and defense, approaching the problem with computational analysis rather than the empirical traditions of locomotive engineering. What they created was arguably the most technically advanced passenger train of its era. The Advanced Passenger Train, designated APT, incorporated active hydraulic tilting, hydrokinetic braking, articulated lightweight aluminum car bodies, and in-cab signaling. The experimental version, APTE, was powered by gas turbines and achieved 152 miles per hour in testing during 1975, setting a British rail speed record that would stand for decades. The production prototype, APTP, used electric traction and could tilt up to 9 degrees from vertical, theoretically enabling speeds of 155 miles per hour on track designed for 90 miles per hour. The tilting mechanism itself was a masterpiece of engineering. Sensors mounted on the leading bogie detected the entry into curves and transmitted signals to hydraulic actuators on each carriage. These actuators pivoted the car body around a point near the roof, tilting the entire passenger compartment inward, while the running gear remained aligned with the track. The system could tilt the full 9 degrees in approximately 1 second, responding to curves faster than passengers could perceive the change. Then everything went wrong. On December 7, 1981, British Rail launched the APTP into regular passenger service with tremendous publicity. Journalists and dignitaries filled the inaugural run from Glasgow to London. By the return journey, disaster had struck. The tilting mechanism on several carriages malfunctioned in the winter cold, failing to right the cars after curves and leaving passengers perpetually tilted. Water had infiltrated the compressed air systems that operated the doors, freezing in the December temperatures and trapping people inside carriages. Some passengers reported severe motion sickness, a phenomenon that engineers had not anticipated. The problem was subtle but devastating. The APT tilted perfectly, compensating almost entirely for centrifugal force. Passengers looking out a window saw the world tilted, but felt no corresponding sideways pressure. The mismatch between visual and vestibular sensation triggered nausea in susceptible individuals, the same phenomenon that causes seasickness. The press dubbed it the queasy rider. Headlines mocked what should have been a triumph of British engineering. Within days, the trains were withdrawn from service. The technical problems were fixable. Engineers discovered that reducing the maximum tilt angle slightly, allowing passengers to feel a small amount of centrifugal force that matched what their eyes perceived, eliminated the motion sickness. The door seals were improved. The hydraulic systems were winterized. By 1984, the APTP trains were running reliably on the West Coast Main Line. completing journeys in record times. But the damage was done. The hostile press coverage had poisoned public and political support. In 1986, British Rail quietly canceled the program, scrapping the trains and selling the patents abroad. The Italians were waiting. Fiat Ferroviaria had been refining their Pendolino technology throughout the 1970s and early 1980s, learning from both their own experiments and the very public failures of the British program. In 1982, they acquired the APT patents for the tilting bogie mechanism and incorporated improvements into their next generation of trains. The ETR 450 entered service on the Rome to Milan route in 1988, followed by the more advanced ETR 460 in 1993. These Italian trains incorporated a critical refinement. Rather than tilting the full amount needed to eliminate centrifugal force, they tilted to approximately 70% compensation, leaving passengers with a subtle but reassuring sensation of cornering that matched their visual perception. The maximum tilt angle was limited to 8 degrees rather than the APT's 9 degrees. This seemingly small difference transformed passenger acceptance entirely. Sweden took a parallel path. The X2000, developed by ASEA and Kalmar Verkstad for Swedish State Railways, entered service in September 1990 on the Stockholm to Gothenburg route. Swedish railways, like British ones, featured extensive curvature laid out in the 19th century when terrain was expensive to move and political obstacles expensive to overcome. The X2000 could not match the raw speed of French trains on their purpose-built high-speed lines, but it could achieve competitive journey times on existing infrastructure at a fraction of the construction cost. The results were remarkable. Before the X2000, Swedish State Railways held just 19% of the Stockholm to Gothenburg travel market, with air and road capturing the remainder. Within 5 years of introduction, rail's market share had climbed to 52%. By the end of the decade, it exceeded 70%. The tilting train had not merely preserved a railway, it had resurrected it. The technology proliferated. Finland ordered tilting trains. Portugal ordered tilting trains. Germany developed the Ice-T variant of its intercity express with active tilt for mountainous routes through Bavaria and Saxony. Switzerland, land of alpine curves, adopted tilting technology for its cross-border services into Italy. Even China, building high-speed lines from scratch elsewhere, purchased Swedish tilting technology for routes where new construction was impractical. And Britain? In 1998, Virgin Trains, the private operator that had won the franchise for the West Coast Main Line, placed an order for 53 tilting electric trains. They would be built by Alstom, which had acquired Fiat Ferroviaria, using technology descended directly from both the Italian Pendolino and the British APT. The trains entered service in 2002, finally delivering the tilting capability that British Rail had promised 2 decades earlier. They were called, with appropriate irony, Pendolinos. The British Class 390. Pendolino can tilt up to 8 degrees, taking curves at speeds 20% higher than conventional trains. Each 9-car set weighs approximately 450 tons and can carry over 400 passengers. The traction motors, suspended from the car bodies rather than the bogies, reduce unsprung mass and track wear at speed. The pantographs, the roof-mounted devices that collect power from overhead wires, feature their own active tilt system, moving in opposition to the car bodies to maintain contact with the catenary, regardless of the tilting angle below. The physics remain the same as when Victorian engineers first banked their tracks. Centrifugal force still equals mass times velocity squared divided by radius. By tilting the reference frame in which passengers experience that force, engineers have effectively widened every curve on the railway without moving a single rail. A bend designed for 75 miles per hour becomes safe and comfortable at 90 miles per hour. Infrastructure laid out when Queen Victoria ruled an empire now carries trains at speeds their builders could not have imagined. Yet tilting trains have not conquered the world. France, Germany, Japan, and China continue building dedicated high-speed lines with gentle curves that require no tilting at all. The train à grande vitesse achieves 200 miles per hour precisely because its tracks have no curves tight enough to require compensation. Building new is expensive, but operating tilting trains is also expensive. The mechanisms require maintenance. The control systems require calibration. The reduced speeds on curves, even with tilt, still cannot match purpose-built high-speed infrastructure. The tilting train represents a compromise, brilliant in its engineering, but limited in its ultimate potential. It is the solution chosen by nations too densely developed to build new railways, too historically constrained to abandon existing alignments, too politically fractured to fund the construction of straight lines through populated landscapes. Britain, Italy, Sweden, Finland, Portugal, and Switzerland chose tilt because the alternative was either impossible or unaffordable. France and Japan chose not to need it at all. There is a preserved APTP at the Crewe Heritage Centre in England. Its blue and gray livery faded, its tilting mechanism frozen in place, a monument to ambition that outran execution. Nearby, every hour, a Pendolino sweeps through the same curves the APT was designed to conquer, carrying passengers who neither know nor care about the half-century of engineering that makes their journey possible. They experience only the result, a slight lean into the turn, a coffee cup that stays where they placed it, an arrival time that makes rail competitive with air. The Victorian surveyors who laid out those curves could not have conceived of what would one day pass over their rails. They built for a world of steam and coal and 30 miles per hour. We have answered their limitations not by tearing up what they created, but by teaching our machines to dance with it, to lean into the turns they forced upon us, to find speed in the spaces between their compromises. The trains still tilt. The curves remain. And every passenger who arrives on time owes a debt to engineers who refused to accept that old tracks meant slow journeys, who looked at a problem designed into the landscape and asked not how to avoid it, but how to embrace it. The tilting train is not the fastest machine on rails, but it may be the most elegant solution ever devised to a problem that was never supposed to be solved.